because they're all the same as number one, just some different functions, some different coefficients, but the work is going to be the same. Also, just be careful with the positives and the negatives. Now that we've done antiderivatives, and now we're going back to derivatives, it's just easy to get those mixed up. So 2 should get positive cosine of 3x, and then the derivative of 3x would have given us a 3. And then number 7, derivative of cosine would have been a negative sine of 7x. The derivative of 7x would be a 7. And then lastly, initially, this would be a negative sine of negative 2x. The derivative of a negative 2x would be a negative 2, so we get a negative negative 2. So that should end up being a positive 2 sine of negative 2x. The reason I have you do this, and this is going to be kind of the theme of what we were doing, or what we're going to be doing this whole set of lessons, is kind of the idea yesterday. Yesterday we talked about, let's take the derivative of sine, and that should be a cosine. And what we now know is, if I now do the antiderivative of this, it should take me right back to where I started. So that's going to be our thought process with all of these. So if I now go to this next set of things here, determine what must be done in order to retrieve the original function. What that means is, let's say I now started you with this, because that's kind of what we're getting at now. Let's say this was what you were given, and I wanted you to work backwards. So if we now wanted to work backwards, what we would want to do first is understand that the antiderivative of cosine would have been sine. So we would have said this is a sine, and then we leave the inside alone like we would normally. But notice how this coefficient in the original function was a 1. And currently we would have had a coefficient of 5 right now. So in order for us to turn this 5 into what it was originally, which is that 1, what we would have to do this is, now whatever this coefficient is, instead of multiplying it, we would now need to divide by that. And when we do that, that's going to cancel out and give us what we started with. So the theme that we're going to talk about a lot today, if we are looking for an antiderivative, and we mentioned it yesterday, if you just think about what that prefix means, what it implies, anti basically means the opposite. We want to do the opposite of what we would normally do in a derivative. So in terms of what we would want to do here, we want to find the antiderivative. Pen work. Of the trig function. But then in order for us to get rid of this 3, to get rid of this negative 7, and to get rid of this 2, so that these all end up with coefficients of 1 here, what we would now need to do is divide. So instead of multiplying by that derivative, we're going to divide by the coefficients. All right, so that's how we can handle if it's sine of 2x, secant squared of 2x. All right, it's just working backwards. So what I want you to do real quick, let's fill these in. The first 2 we've dealt with periodically here recently, but these 4 we haven't really had to work with for a while. I guess this one we did yesterday. But all this is saying is the antiderivative of sine is a negative cosine, and then whatever kx is, we have to now divide by the k instead of multiplying by it. Antiderivative of cosine is sine. You leave the inside alone. We've got to divide by that coefficient. So this one we actually did do yesterday. The antiderivative of secant squared is tangent, so you're going to leave that alone. And then since we're now doing an antiderivative, we're doing the opposite of what we would normally do in a derivative. In a derivative, you would have multiplied by k. So in an antiderivative, we need to divide by k, and then plus or constant. All right. So real quick, see if you remember the next 3, not ones that we've had to deal with recently. And then understand how to handle the k as well. And then again, be very, very careful if it's positive or negative. Let's see if you remember all of these. All right, Carter, what do you think, Carter, for the cosecant squared? What did we take the derivative of to get a positive cosecant squared?
Is it cotangent kx over k?
All right, so cotangent kx. My pen's not liking this right now. Let me try a new pen.
Plus c.
Good. We definitely need that plus c. And then do we all agree with this? We have some differing opinions on this one. If I ask you the derivative of cotangents, do we remember what the derivative of cotangent was? Isn't that, yeah, it's a negative cosecant squared of x, right? So if I have a positive cosecant squared of x, what that would have told us is our cotangent has to be negative, okay? That's the biggest error that I'll see when we do these, is just knowing if it's positive or negative. Because again, we're still going to do plenty of problems where we need a derivative. Now we know antiderivatives, and we want to keep those things straight. All right, the next one, secant squared x tangent of x. Farah, what do you think, Farah?
So I just said the secant, and then in parentheses the x k, and then over k plus c.
Good. This one's a little bit easier because there is no sign change. The derivative of secant is a positive secant, so we don't have to worry about any tricks with the signs or anything. But good, again, we haven't done this one in a while. What we took the derivative of to get a secant tangent is a secant. All right, and then the last one here, Lindsay, what do you think, Lindsay? What did we take the derivative of to get a cosecant cotangent?
A negative cosecant k over x divided by k plus b.
Good. The derivative of cosecant would have been a negative cosecant cotangent. So since our cosecant cotangent is positive, that meant the original cosecant had to have been negative. All right. So that's how we handle those if we have a trig function. And keep in mind, this only works, every single one of these models has an exponent of 1 right now for the x. If this x has a power other than a 1, then we're dealing with something much more involved, but it's not something we're doing right now. So that only will work if it's 10x, 8x, 4x, and the x has a power of 1. Okay? All right, next ones. Let's see. See if you remember 5 and 6. I ask you to take the derivative of 5 and 6. Let's see what we think. Come on. Okay. Because then what I'm going to ask you to do, whatever we just did for the derivative, the antiderivative, you would do the exact opposite. So as you do that, kind of think, all right, what 2 things did I just do? The antiderivative, I'm going to do the opposite. All right. This we have dealt with. Last chapter, we had to do a number of these still. So hopefully we still remember E reproduces itself. And then when we take the derivative, we multiply by the derivative of our exponent, which is 3 in this one, and then 5 in this one. So now what we want to think about, what would we need to do to go backwards? So if I put a little indefinite integral in front of this and told you to now go backwards, first obvious thing is if the derivative of E produces itself, then that means the antiderivative of E would have to reproduce itself. So we're going to rewrite the E to the 3x. But if we ultimately need a power of 1 right here, the way we're going to do that is now by dividing by whatever that coefficient is. So instead of multiplying by 3, we now need to divide by 3. Same here. This would reproduce itself, but in order to get that 5 to go away, we would have to divide it by the coefficient of x, and then that's how we're going to get that power of 1. If you look at the bottom here, this rule is written for you. All right. Keep in mind the format of this. This x has to simply have a power of 1 right now. If it doesn't have a power of 1, all right, this right here, then this is a different little method that we haven't talked about just yet. All right. All right, next one. If I ask you for the derivative of that, this is the one that sometimes causes some raised eyebrows the first time around. So do that derivative. And we should all get 1 over x, and then the derivative of x would just be a 1. And since it's a 1, we don't really need to show it. But here's what you now need to understand. We hopefully understand if I give you y equals sine of x, the derivative is cosine of x. So when we do the antiderivative of something, what we are asking ourselves is, what did I take the derivative of to get this? So what I took the derivative of to get a cosine would have to be what I started with, and that is a sine. If we apply that thinking to this problem, what that means is the antiderivative of 1 over x, you are thinking, what did we take the derivative of to get that? Didn't we just take the derivative of a natural log of x in order to get the 1 over x? All right. Then this needs an absolute value. We'll elaborate on that in due time. And then that's our antiderivative of a 1 over x. Now, this is different. So here's another reason why this causes a little bit more trouble. Let's say I gave you this problem here, 1 over x squared plus 1 over x. Yesterday, I said, take a few seconds, rewrite this problem. That's what we would have done yesterday if I had given you this, which I didn't give you one that had a power of a negative 1, because it would have been a problem. But let's say we do our power rule like we did yesterday. So with this one, I would have added 1 to that power, and then we would divide by that. So that's fair, nothing tricky there. Plus, now think about what happens when I add 1 to this power. A negative 1 plus 1 would have given us a 0. And then we have to divide by that new power of 0. And then can we divide by a 0? No. So that's how we gotta understand when we get this 1 over x, we've got to recognize this as the derivative of a natural log. That's got to be its antiderivative. All right. That's when you want to be careful of. That's one that people tend to mess up. If you go down here, then that's what we have here. What we took the derivative of to get a 1 over x is the natural log. And then this absolute value is pretty critical. The reason for that, this you might want to draw in. Think about what 1 over x looks like. So the graph of 1 over x looks like this. If I want you to find the area of 1 over x dx from -3 to a -2, although maybe we're not quite ready for this because we haven't done definite integrals yet. We'll revisit that. Just take my word for it right now. Make sure you have that absolute values there. You don't actually know how to do that just yet. So whenever we do the antiderivative of 1 over x, when we get to this little quiz you're going to take, when you do this, when I grade work, if those x's do not have absolute values, that's going to be a cheap point off. Okay, so make sure that those are there. Once we get to a little bit later here, when we evaluate a definite integral, we'll talk about why those are pretty critical. Okay. All right, 8. See if you remember this one. This was on your last cumulative assignments. So hopefully we now remember this from a long time ago. Because then whatever you do for the derivative, the antiderivative, you're going to do the opposite. All right, so that's why we need to know all of our derivative rules so that we know when we do the antiderivative, you're going to be doing the opposite of what we would normally do. All right. All right, anybody remember this one? You did just do this on that assignment. No brave souls. All right, so this is like e to the x. Remember what you would do for e to the x, right? Let's say I put e to the 2x. Don't we take the derivative and then multiply by the derivative of the exponent? So this is still an exponential function, so this is going to repeat itself. We still multiply by the derivative of the exponent, which is a 2. But then remember how there was this third part? There was a second part to this here in the middle. And what we multiplied by also was the natural log of whatever the base was. And in this case, that base is a 4. So that's our derivative. The reason we don't have to do it with an e, I think I've shown you this, I don't remember. These are really the same functions, right? Exponential, exponential. So I could do the same thing here, multiply by the natural log of the base. But it's sort of pointless, right? Because isn't the natural log of e just a 1? So we don't need to do it if the value is a 1. But as soon as it's not a natural log of e, then that needs to be shown. All right, so that's our derivative. So if we multiply, so I already have this highlighted, in a derivative, we multiply by the natural log of the base, and we multiply by the coefficient of x. Antiderivative means you're going to do the exact opposites. So if we now go to down here, I don't think I have this one filled in. Oh yeah, I do. If I have this function here, then it's going to repeat itself, but now you're going to be dividing by the natural log of the base. And instead of multiplying by that k, we now need to divide by that k. Right? So if we're multiplying in the derivative, we're dividing in the antiderivative. All right, the last two. Which one did we do yesterday? This one we did yesterday, so this one should be familiar to us. This is the 1 over, we always said 1 plus u squared. The u is always your coefficient. So our coefficient or not our coefficient, our composite is an x, and then we would do the derivative of x, which is just a 1. So that's our derivative. So let me get rid of these parentheses. So the one that I gave you yesterday looked like this, and then we just had to recognize this as the derivative of an inverse tangent. All right. So come down here. These I did not fill in. So if you ever come across one that looks like this, we've got to recognize that as the derivative of the inverse tangent, which means its antiderivative is inverse tangent. All right, and then the last one, inverse sine. Inverse sine's derivative was 1 over the square root of 1 minus, and then we said u squared. Just like the inverse tangent, u is your composite. In that case, it's an x, and then the derivative of x would be a 1. So if we get rid of all the unneeded stuff, I don't need to times by 1. This doesn't now need a parentheses. If we ever come across this, you would just need to understand this is a result of taking the derivative of an inverse sine. So if we go down here, when you see this combination, you need to recognize that as the derivative of inverse sine. Therefore, that's your antiderivative. And then the last one, I didn't give you a derivative, but we hopefully recognize this as the derivative of inverse secant. Hopefully you also recognize we've only done 3 of the 6, right? We didn't do the inverse cosine. The reason we don't need to do the inverse cosine is because isn't the inverse cosine just this? So when you come across something like this, there's one of 2 options. You could just say this is inverse cosine. So that's fair game. Or, actually, we're going to talk about that in a second. What we can do also, similar to when we do derivatives, we can actually pull that negative one out. We talked about this a little bit with our Riemann sum. And can't we very quickly turn that into an inverse sine? So we could also call this a negative inverse sine. Either one of those 2 answers would have been okay. All right, when we do those. So you're going to get some of those on the next page when we start cranking some of these out. Those are pretty much all of your rules in combination with what we did yesterday. And then here, these are all the types of functions we've taken the derivative of. So we now need to be able to go backwards. All right, and then here's that little rule I was just mentioning now. So the constant rule is, and here's where this will really apply. The most obvious would be, let's say I gave you an antiderivative and I put a 3 in front of a cosine. We could if you want, and you don't have to. And again, as we do more and more of these throughout the year, you'll know when maybe this is advantageous. We could pull that 3 out if we want, do the antiderivative, and then multiply by 3. It's sort of pointless in this sense. You don't need to rewrite it. What it's really just saying is if you have a constant, we can just drop it down just like we do a derivative and then do the antiderivative of the second part, okay? If we have a negative coefficient, similar, we could, if we want, take this negative, ignore it, just put it out in front of everything, and then multiply by it at the end. It's up to you. And then what this is now saying, the sum and difference rule, is just saying, like if we look down at number 1, see how I'm adding 3 different terms together? So first one, second one, and the third one. We could, if we want, split those into multiple integrals. Most of the time it's pointless. It's just a waste of time. It takes up more work than we really need to. But just know that it is possible, okay? And when we're dealing with like this here, we don't want to have to write this as 3 integrals. What this is really saying, the biggest thing that this is saying, We can only go term by term if we're adding or subtracting. So if I give you a function like this, so write this out, this I want you to see. Let's say I give you x plus cosine of x, and I want you to do the antiderivative of this. Move this over a little bit. Versus x times cosine of x dx. Notice again, we can only do them individually if we are adding or subtracting. So for this one, I can go ahead and do x squared over 2 plus sine of x, and then plus our constant. We absolutely cannot do this, so this will not be true. We can't now go x squared over 2 times a sine of x. It does not work like that. And you could prove it to yourself very quickly. If we took the derivative of this guy, it would give us what we started with. But if you do the derivative of this one, which now requires a product rule, it will not give you what you started with. So as long as we're adding or subtracting, then we just can do the terms individually. And that's largely what we have at the bottom of this page now. All right, so now I'll just crank out a bunch of these and see if you remember all the stuff from the front page. So with this one, we could split these up, but we don't really want to. Again, as we do more and more things throughout the year, you'll see when that's going to help. But we could, if we want, write 3 different integrals. But since they're all adding, subtracting, we just go term by term. So this is from yesterday. We add 1 to the power and then divide by the new power. The constant rule, what it effectively is saying is the constant you can just drop down. So just like a derivative, the 2 we can just drop down. The antiderivative, what we took the derivative of to get a secant squared is tangent. So it's just 2 tangent of x. And then the antiderivative of 2 is 2x. And then do not forget your c's come quiz time or on the assignment. Okay, number 2. We talked about these on the front page. Let's see what we recall. Try number 2 real quick. See if we can get these. If you need to flip your paper over and look, fine. Let's see what we think for number 2. Okay, and then let's see if you get what I get. So the 3 is a constant, so that initially just gets dropped down. So we just rewrite it. So there's our 3. Maybe if my pen will work. Come on. There we go. And then for the derivative or the antiderivative of the exponential function, it's going to repeat itself. In a derivative, you would have multiplied by that 3. Since we're doing an antiderivative, you now do the opposite of that, which is divide by 3. So then we're going to divide that by 3. So then these guys obviously cancel, and we're just going to end up with e to the 3x. And then this one again, now that we've seen it, but this one tends to be one that people will miss. What we took the derivative of to get a 1 over x would have been the natural log of x, and then we need to include those absolute values, and then plus RC. All right. And then that's it. All right, so 3. If I can move this over. This guy. Now, I deliberately put these back to back because people tend to, in the first day or two, once they start seeing 1 over anything, so like 1 over root x, people start thinking, oh, that's a natural log of root x. The only time you're going to get a natural log is if it's 1 over x to the power of 1. That's the only time we get that natural log. We would have done this one yesterday before we revisited the natural log. This has an x to the 1/2 power in our denominator. So if I move that up, that's just an x to the negative 1/2. We do our power rule as we did yesterday. So add 1 to that. So we're going to get a positive 1/2. When you divide by 1/2, that's the same as multiplying by 2. And then add your constant. All right, this one I typically would rewrite. So just 2 root x and then plus c. Okay, 4. We know it's a cosine. We just want to know, is it positive or negative? So you're thinking, what do we take the derivative of to get a positive sine? that should be a negative cosine. And then now that we're doing an antiderivative, we no longer multiply by that 3. We have to divide by that 3. And then plus c. If that one makes sense, number 5 is pretty similar. The only thing I did is I gave you an extra constant. But we've talked about how that you just drop down. You ignore it initially. So you just drop that down. And then same exact function, sine and sine. Its antiderivative is a negative cosine. We'll leave the inside alone. And we now know we divide by that coefficient. So now we take whatever that initial constant was, and we just multiply it by that negative 1/2, so that we get a negative 3 ultimately for that coefficient. And then that ends up being our answer. All right. So number 6, go ahead and do number 6. Should be similar. Although there isn't, yeah, just do that one. I won't give you any hints. Okay, I don't know what it is with fractions, but here's what tends to happen with number 6. So if you look at this problem here in the middle that I just added, when we do something like this, and we just did a bunch in a row, the antiderivative of cosine is sine. And then think about when we divide, don't we only divide by the coefficient? We don't divide by like twice x, we just divide by that coefficient. Because for whatever reason, when people start doing this guy, they do a sine and then they leave the inside alone. But then what I often see when we do these in class and I walk around is people like putting an x over 2 in our denominator. We only put the coefficient of x in our denominator, and the coefficient is only, get out of there, a 1/2. X over 2 is the same as a 1/2 x, so we should only be dividing by a 1/2, and then plus your constant. So that we get 2 sine of x over 2 plus c. That would be our final answer. Okay. All right, number 7. Give that one a go. See what we think there. All right, first term should be pretty simple. The 2 you drop down. The antiderivative of secant squared is going to be a tangent. The next term, it's really up to you how you want to handle this. Some people may look at this and think, all right, I'm going to leave this as a negative 5. I'm going to drop that negative 5 down, and then I'm just going to multiply by whatever this would be. So if you approach it that way, then you're kind of treating the cosecant as a positive cosecant squared. And if you do it that way, then that cotangent you're going to come up with is a negative cotangent of 5x. And then you'd obviously have to divide by 5. Other people, and this is probably where you'll eventually get to if you didn't do it in the first place, so I think it's a little simpler, a little easier to understand, is just understand this right off the bat, the minus sign is a negative cosecant squared. So if that's a negative cosecant squared, we could just right away change this into a plus, and then 5 cotangent of 5x divided by 5. Both of them, because we create the double negative up here, should end up with this plus 5 as our final sign, or plus cotangent anyway. All right, and then I forgot my c, and then we do our plus c. So it's up to you how you want to handle these. If you want to ignore it and then just create a double negative, if you want to consider that a negative cosecant squared, that's probably a little bit better. All right. Okay, number 8. We've already done a few of these. I want to make sure we don't have to borrow time. These repeat itself. The 2 comes down, e repeats itself. We now divide by 4. And then now we've done this a couple of times. We just have to recognize this as the derivative of a natural log of x, and then plus our constant. So final answer should be that. Okay. All right, number 9. Do number 9. The first one should be easy. It's going to repeat itself. And then you've got to divide by the 7. And then I'm just curious how you're going to handle that next one. All right. Aaron, what'd you do for that second one, Aaron? What do you have here?
I have minus inverse tangent of x.
All right, good. That is correct. However, anybody do it differently? How else could we have written that? Anybody else write it a different way? Which would be equally correct, so don't think I'm asking you because it's wrong. Somebody popped in. Yeah, Eva. What you got, Eva?
A 7 to the 7x plus the inverse of cotangent of x plus
Good.
2.
Those are both equally correct. Because doesn't the derivative of inverse cotangent give us a negative 1 over 1 plus x squared? So both of these are fair game. That's why just multiple choice, quiz, test, whatever, be able to recognize either one of those, okay? All right, next ones. I'm going to start to expedite this a little bit. Just be careful with your signs. We know this is a cosine. The antiderivative of sine is what we take the derivative of to get a positive sign, and it should be a negative cosine. So that's a negative 4 cosine of x. Here I'm going to treat this right away as a negative cosine. So the derivative, or what we took the derivative of to get a negative cosine, would have been a negative sine. So we just get negative 3 sine of x, and then plus our constant. Actually, I lied. I want you to try one more. Actually, the next few are all ones that I want you to try. Try number 11. E to the 8x, you better be able to do that one at this point. We've done plenty of e's today, so e to the 8x divided by 8. But then recall how we did that on the front page. If you need to look on the other page, feel free. All right, so in number 11, these are both exponential. So this 5 to the 9x and e to the 8x, those are both exponential functions. So just like that e, you have to rewrite it, and then you have to divide by 9. That's how they're similar. The only thing that's now different is we have to also divide by the natural log of whatever the base was, and in this case, that would have been a 5. Okay. So just an old derivative we have to remember now for the sake of taking our antiderivative. Okay, 12, I'd like you to take a second and see if you can get that one. You got six minutes to do 2 problems to see what you get for 12. if you look at what I did, I split these up. This is not necessary. I think after you see me do this one problem, you won't necessarily need to do this again in order to see how this plays out. But that is one of our rules. As long as I'm adding, which we are, I could really just split these into two different integrals. The reason I'm going to do that is then we can also use the rule, and we haven't done it yet, where let's say I give you 3 cosine of x. We said we could, if we want, rewrite this with the 3 out in front. It's sort of unnecessary. It's kind of a waste of a step. We don't necessarily want to take our time to do that. But for a problem like this, the first time seeing it, it might be to your advantage to do that. Because I can take this 3, can't I take this 3 out? And wouldn't that just leave me with a 1 over x on the inside still? And when you see it written like that, now we better all be like, okay, yeah, that's not as hard as maybe I thought it was, because that just means this is 3 times the natural log of x. You can test it. If I ask you to take the derivative of 3 ln of x, wouldn't that give you a 3 times 1 over x, which is 3 over x? So really, if you ever get like 5 over x, 10 over x, these are all natural logs of x's. The numerator is just your coefficients, right? So not uncommon. So any constant over x is still the natural log of x. Your numerator is just going to end up being your coefficient. The other one hopefully wasn't too bad. Drop the 3 down. Think what we took the derivative of to get a secant tangent, and then that should be a secant. And then you leave the inside alone. Divide by that 6, so that we get secant of 6x once we reduce, divided by 2, and then plus your constant. All right. (13) similar. This is very much like everything that we have done. Just kind of cut to the chase to make sure we get it done. If this wasn't here, isn't that just a natural log of x? Even if it is there, as long as we're adding or subtracting a constant, so that's what we're doing. Here's the x, and we're just going to subtract that constant. This is still nothing more than x, a natural log of x minus a 6. You could test it real quick. If I ask you to take the derivative of this, wouldn't that give us 1 over x minus a 6 times a 1? So this does give you the original function that we started with. So even if I give you like 1 over x plus 10, that's still just the natural log. It's just an x plus a 10. As long as your exponent is a 1, as long as that coefficient is a 1 for the x, it doesn't matter what we're going to add or subtract. That's still just our natural log. All right. Okay, I kind of take matters into my own hand here. That's why I give this assignment, so you just crank out a bunch of these. By the time you get done with that assignment, usually most people are feeling pretty good about it. All right, you get the patterns down, and you get everything figured out pretty well. So just recall you have this. It'll be due Monday night. So even if you forget on Monday, I'll give you a reminder on Monday. Just make sure it's due, or make sure it's done by that night. All right. All right. That's all I got. We actually finished again without rushing too much. So have a good weekend. If you have any questions, you got a minute or two, hang out. But we'll see you on Monday.
What does the mean value theorem have anything to do with anti-differentiation in this one?